Hi, I'm Benny, and I've dedicated my life to understanding the universe, with the hope that one day I'll get the chance to hop on a rocket and see it for myself. Growing up, I was always looking up, not just at the stars, but at the endless questions they sparked. I'd spend hours wondering what was out there, how it all worked, and if I'd ever get the chance to see it for myself. This is Space Bites, where I take the overwhelming, mind-bending world of space and break it down into small, easy-to-digest pieces. Think of it like snacking on the cosmos, quick, simple, and deliciously full of wonder, so anyone can understand and enjoy it no matter their background. Why? Because every atom in your body was forged in the heart of a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of it began in stellar furnaces, which means, quite literally, the universe is in you. You are the product of cosmic alchemy billions of years in the making. The same processes that built galaxies also built you, linking your existence to the cosmos itself. Hello, everyone, and welcome back to another episode of Space Bites with Benny. It's me, Benny, your favorite nerd. Today, I want to talk about my favorite particle of all time. But before I can tell you what it is, I'm going to give you the map. Because physics has a habit of dropping you in the middle of a story without really telling you where you are. And I'm not going to do that to you. So let's start at the very beginning. What is everything made of? So everything you have ever touched is made up of atoms. The chair you're sitting on, the air moving through your lungs, even your own body, it's all made up of atoms. And for a long time, scientists assumed the atom was the smallest thing that ever existed. The word atom itself, comes from the Greek atomos, meaning uncuttable, something that's indivisible, the end of the line. But it isn't. So the atom actually has an inside, and at its center is something called a nucleus, a dense core that is made up of protons and neutrons. Around that nucleus is a kind of blurred cloud of orbiting electrons. This is the picture that most of us got in school, and it's kind of correct. But if you go deeper, protons and neutrons themselves are made of smaller particles called quarks. There are approximately 3 quarks per proton, 3 quarks per neutron, held together by particles called gluons, which carry the strong nuclear force, which is the most powerful force in nature between them. And then there are other particles entirely that don't go into building the nucleus at all, and the electron is one of them. So it belongs to a family called leptons, and these are particles that feel certain forces but don't participate in the building of the atomic nucleus. The electron has an electric charge, which is negative, and it sits in orbit around the nucleus. It doesn't make up the nucleus, but rather it orbits around it. And it governs chemistry, and it carries electricity through wires. The electron has cousins. And these two cousins, are heavier versions of itself, and they're called muon and tau. And they're identical to the electron in every single way except for their mass. And paired with each of those, the electron, the muon, and the tau, is a partner particle that is neutral, almost ghost-like, and completely invisible to the rest of the universe. So those partner particles are called neutrinos. And this is where we come to the start of the episode, talking about my favorite particles of all time, which are neutrinos. And there's 3 of them. There's the electron neutrino, the muon neutrino, and the tau neutrino. And together with the quarks, the gluons, the photons, and a handful of other particles, they make up what we physicists call the Standard Model, a complete inventory of the fundamental building blocks of the universe. 17 particles in total. And so the neutrino is on that map, but it sits in a strange corner of it, and that is what makes it my favorite. So before I tell you what the neutrino actually is, or what it actually does, I'm going to read you something. In 1960, the American novelist John Updike, he wasn't a physicist, he was a writer, published a poem called Cosmic Gall. Neutrinos, they are very small. They have no charge and have no mass and do not interact at all. The Earth is just a silly ball to them through which they simply pass, like dust maids down a drafty hall or photons through a sheet of glass. So the name neutrino was coined by Enrico Fermi, And he really was a central figure of 20th century physics. And he named the neutrino in Italian, which means little neutral one. So Updike's poem is almost completely correct. The neutrino has no electric charge, it's neutral, hence the little neutral one, as the name says. It has almost no mass, and for decades we assumed it had exactly zero mass, which is what Updike's poem reflects. We now know that it actually has a tiny bit of mass, but it's so small we still can't measure it precisely. And so what we know is that it is at least 1,000,000 times lighter than an electron, which in itself is already one of the lightest things in existence. It barely interacts with anything. That's why I described it as ghost-like before. Of the 4 fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, the neutrino only responds to 2. The first is gravity, which at the very, very small scale that it's at is negligible, and the weak nuclear force, which controls radioactive decay and certain nuclear reactions. And it operates only at short distances. So it only allows interactions between 2 things that are within a very small distance. However, it ignores electromagnetism and ignores the strong force. So here's a number that kind of wraps all this information together. If you fired a neutrino at a wall of solid lead 1 light year thick, so you have a wall of metal and it's about 9.5 trillion kilometers thick, so 9.5 trillion kilometers of dense metal, and you fire a neutrino at it, it would have a roughly 50-50 chance of passing straight through without interacting with a single atom. So it just passes through like a ghost. And there's a 50-50% chance of this. So a whole light year of lead, a whole 9.5 trillion kilometers of dense metal, and the neutrino has a 50% chance of passing through without interacting, without bumping into or touching any of the atoms in this very dense metal. The Earth, as Updike wrote, is just a silly ball to this very cool neutrino. So where do neutrinos come from? They're not exactly rare. They're actually one of the most abundant particles in the universe. And right now, approximately 100 trillion neutrinos pass through your body every single second. And the overwhelming majority of them actually come from the sun, which produces neutrinos continuously through nuclear fusion. And nuclear fusion is the process by which hydrogen atoms fuse together to form helium atoms. And so this releases energy in the form of both light and neutrinos. So the sun produces these neutrinos, and it does this through nuclear fusion, which is the same process where 2 hydrogen atoms fuse together to form helium, and this formation of helium releases energy as light and as neutrinos. So the fusing of hydrogen to form helium releases energy, and this energy has 2 forms, which is light, photons, and neutrinos. And for every photon of light that the sun emits, it produces roughly 2 neutrinos. So it's a 2-to-1 ratio. For every 1 photon, there's 2 neutrinos. And so while photons actually have quite a difficult journey because they're generated inside the sun's core, and they immediately begin colliding with other particles because photons interact with other things. They're not ghost-like. Photons actually interact. So they start colliding with other particles. They bounce, they're being absorbed, they're being re-emitted. They fight their way outward through dense plasma in the sun. And that journey from the sun's core to its surface takes between 10,000 and 100,000 years. Like, just take a second and really think about these numbers. You have the sun, and at the sun's core, you have nuclear fusion. Hydrogen atoms fuse together to form helium. This energy is released in both photons and neutrinos. It takes these photons that are being produced at the core of the sun 10,000 to 100,000 years to leave the core of the sun because of how much they interact, because of how much they bounce and are absorbed and re-emitted by other particles inside of the sun. However, neutrinos leave that same core and reach the Earth in 8 minutes. So it takes photons to leave the core 10,000 to 100,000 years. And it takes neutrinos 8 minutes. 8 minutes to leave the core of the sun and to reach Earth. Because nothing slows them down, because they don't interact with anything, and they can pass through the entire sun, which is 1.4 million kilometers of a star, without being stopped. So at night, when the sun is on the other side of the planet, those neutrinos pass through an entire side of the Earth before they pass through you. Because they're being produced in the sun, they pass through the entire Earth before they can get to you, because you're on the opposite side of where the sun is. So the Earth is no more of an obstacle than the air is in this room. Beyond the sun, neutrinos are produced in nuclear reactors, also in the upper atmosphere when cosmic rays hit, and in the cores of other stars, and most dramatically in supernovas. When a massive star in space exhausts its nuclear fuel and collapses, it explodes with a violence that is difficult to put into language because it's so violent. The energy released from the star exploding, the energy released in the first 10 seconds, exceeds what our sun will be able to produce across its entire 10 billion year life. And 99% of that energy is carried away by neutrinos. This is just absolutely amazing. I mean, if you think about the numbers, when you think about how long and how large and how violent all these processes are, I think it's in a way it's very beautiful, but it's also kind of mind-blowing. So I'll give you an example. In 1987, a star in a nearby galaxy in the Large Magellanic Cloud, which is 160,000 light years away from Earth, exploded. So a star exploded. And so the neutrinos from that explosion arrived at Earth and were detected by 3 separate underground observatories. So we have detectors on Earth that are there to observe neutrinos, and 3 of them detected the arrival of the neutrinos from this explosion, the star explosion. And here's the craziest part. The total number of neutrinos detected across all 3 was 24. 24 neutrinos. From a very violent explosion of a star, only 24 neutrinos were detected, even though we used 3 different underground observatories. 24 neutrinos detected from a torrent that passed straight through the planet. And those 24 gave us the first direct observational confirmation of how supernovas work. And they were enough to test and confirm decades of theoretical physics. So I mentioned where neutrinos come from, and they come from the core of the sun, they come from nuclear reactors, and they come from the upper atmosphere. I also said they come from supernovas. They come from the explosions of stars. I gave an example of a star that exploded in 1987, and I already mentioned that about 100 trillion neutrinos pass through your body every single second. So we already know that they're very abundant. When a star explodes, 99% of the energy from the explosion is carried away by neutrinos. However, we only detected 24. So there's a discrepancy here between the number of neutrinos that we know exists and between the number of neutrinos that we can detect. Which brings us to the 4th section of this episode, which is, how do we detect the undetectable? How do we detect something that doesn't really interact with anything else at all? And the answer is that neutrinos do occasionally interact with other things. They do occasionally interact with matter, but not very often. But occasionally enough that if you have enough matter and if you wait long enough, a neutrino will very rarely collide with an atomic nucleus. So it will very rarely collide with the nucleus of an atom. And when it does, that collision produces a faint burst of light called Cherenkov radiation, which is a brief blue glow caused by charged particles moving through a medium faster than light moves through that same medium. And it is one of the only physical signals we have, or it's one of the only physical signal that a neutrino leaves behind. So to catch these events, you need enormous volumes of matter, extremely sensitive light detectors, and complete isolation from anything else that might produce a false signal. So we have the Super Kamiokande detector in Japan, which is a cylindrical steel tank 40 meters tall and 40 meters across, containing 50,000 tons of ultra pure water. And the water has to be pure because we don't want to have something else contaminating the water, which might lead to a false signal that makes us think that we detected a neutrino when actually it's just a water impurity. And the walls are lined with 11,000 of what we call photomultiplier tubes. And these are instruments that are capable of detecting a single photon of light. The entire detector sits in a zinc mine under a mountain around 1 kilometer underground, because again, we want it to be super isolated from anything else that might interact with it. So we put it underground. And it's kind of like shielding, because at the surface, the atmosphere is constantly bombarded by cosmic rays, high energy particles that arrive from space, which would register as false signals and completely overwhelm any neutrino detection. And a kilometer of rock blocks almost all of that, leaving only the neutrinos, which pass through the rock as easily as if they were passing through nothing. The IceCube Neutrino Observatory at the South Pole is another example, and it takes a different approach than the Super Kamiokande in Japan. Rather than building a tank, IceCube uses a cubic kilometer of the Antarctic ice sheet itself as the detector. Thousands of sensors are suspended in the ice, drilled down to about a depth of 2,500 meters, where the ice is ancient, clear, and completely still. And it sits in permanent darkness at temperatures far below freezing and waiting and watching for flashes of blue light in the ice. And these aren't small engineering projects. They are a representation of decades of work, enormous international collaborations, and instruments of a precision that is very hard to comprehend. And all of this is just to catch a particle that by nature does not want to be caught. Okay, so now we're really getting to the core of why I love these particles so much. And so let's talk about the solar neutrino problem. In the 1960s, physicist Ray Davis constructed one of the first neutrino detectors, a tank containing 380,000 liters of a common dry cleaning fluid that is called perchloroethylene, a common dry cleaning fluid. And it was buried 1,500 meters underground in a gold mine in South Dakota. His goal was to count neutrinos arriving from the sun. Based on well-established models of how the sun produces energy through nuclear fusion, physicists could calculate exactly how many neutrinos it should be producing, and therefore how many Davis should be able to detect. He ran the experiment for years, and the number he counted was consistently about 1/3 of the predicted value. So he built this. So Ray Davis constructed one of the first neutrino detectors, and based on math and physics, we were able to calculate how many neutrinos his detector should detect, or how many neutrinos the sun should be producing. And so Ray Davis ran the experiment for years. However, the number he counted was consistently about 1/3 of the predicted value. And so obviously this is a serious problem, because either the models of how the sun works were wrong, or something was happening to the neutrinos between the sun and the earth. So for 3 decades, for 30 years, this discrepancy, which we call the solar neutrino problem, was a very significant open question in physics. And the resolution to this came around in the late 1990s and early 2000s. And it really allowed us to understand a little bit more about the neutrino. And it turns out that neutrinos weren't disappearing, they were actually changing. So quantum mechanics allows for a phenomenon called neutrino oscillation. Because the 3 types of neutrino, electron, muon, and tau, have slightly different masses, and because quantum particles can exist in a superposition of states. So more than one way of existing simultaneously. A neutrino produced as one flavor, and flavor here refers to electron, muon, and tau, the different types of neutrinos. When a neutrino is produced as one flavor, it does not stay as that flavor. As it travels, it transitions between all three, cycling through them, oscillating between different flavors continuously. The sun produces electron neutrinos. Davis's detector was only sensitive to electron neutrinos. By the time the neutrinos arrived at his tank, 2/3 of them had changed into muon or tau neutrinos, which his instrument could not register. They were there, he just couldn't see them. That's why he was continuously only detecting 1/3 of the neutrinos. The confirmation of neutrino oscillation resolved the solar neutrino problem and had an immediate consequence for the standard model, because neutrinos must have mass for them to be able to switch between types. A particle with zero mass travels at exactly the speed of light, and it cannot oscillate. The mathematics just doesn't permit it. So the fact that neutrinos oscillate between flavors, between mass, between types, is direct proof that they have mass, however small. So this was unexpected. The original standard model had assumed that neutrino masses were zero. The solar neutrino problem forced us to revise that idea, and it was a revision of our most fundamental description of matter. So Ray Davis was awarded the Nobel Prize in Physics in 2002 for his work. And it also happens to be the year I was born, which kind of plays into this whole neutrinos are my favorite particles. So the experiment that Ray Davis ran in a gold mine in South Dakota, counting the absences where neutrinos should have been, turned out to be one of the most consequential physics experiments of the 20th century. So just to recap, Ray Davis in the 1960s constructed a neutron detector. His goal was to count neutrinos arriving from the sun. Based on well-established models of how the sun produces energy through nuclear fusion, physicists could calculate exactly how many neutrinos the sun should be producing, and therefore how many Ray Davis's detector should detect. He ran the experiment for years. However, he was consistently only measuring 1/3 of the predicted value, and this is called the solar neutrino problem. And it turns out that neutrinos were not disappearing, but they were changing. And this is due to a quantum mechanical principle that allows for something called neutrino oscillation. Because there's 3 types of neutrinos, electron, muon, and tau, and they all have different masses, and because quantum particles can exist in a superposition of states, so they can exist in more than one state at the same time, a neutrino produced as one flavor, so a neutrino produced as a tau neutrino, for example, doesn't stay as a tau neutrino, but can also change into an electron or a muon neutrino. This means as it travels, that same neutrino oscillates, it moves between existing as all 3 of its different types. And it cycles through electron, muon, tau, electron, muon, tau. It oscillates between existing as these different things at the same time. And Ray Davis was awarded the Nobel Prize for this work in 2002. And again, this plays into why I love these particles so much. There's just so much more to them than meets the eye. They're non-traditional in a sense. It keeps making our theories wrong, and then it forces us to build better ones. When we thought neutrinos had no mass, they proved to have mass. We assumed it had a fixed identity, but it actually changes identity across 150 million kilometers of empty space. We assumed that we understood everything the standard model told us, but the neutrino told us that we actually didn't. And there are things that we still don't know about it. We don't know that it's exact mass, only that it's non-zero and extraordinarily small. We don't know whether the neutrino and its antiparticle are the same thing or different. We don't know whether there are additional types of neutrinos beyond the 3 that we've detected. And finally, the neutrino sits in this unusual position in physics. It's described by the Standard Model, which is a very rigorously tested theory, and yet it's already broken that model in a significant way, and it may break it in others. Here's another cool part that I find striking about neutrinos. 100 trillion of them pass through your body every second, and they've been doing so your entire life. They carry information from the cores of stars, from the deaths of supernovas, and from the first moments of the universe. That information is encoded in their properties, their energies, and in their direction of travel. And they pass through your body carrying all that information, and they don't leave a trace. The instruments that we built to catch them, these tanks of water under mountains, the cubic kilometers of Antarctic ice, these are very precise and ambitious scientific instruments ever constructed, and we built them to detect neutrinos. And the entire point of these instruments is to intercept something that does not want to be intercepted, to read a message that was never meant to be received from these neutrinos. It takes them 8 minutes to travel from the core of the sun to the Earth, while it takes photons hundreds and thousands of years. There's just something so extraordinary and mind-bending about what little information we already know about neutrinos, and there's so much more that we don't know. 100 trillion neutrinos pass through you right now. They arrive from the sun and from distant supernovas and from the early universe itself. They have no charge, they have almost no mass, and they interact with almost nothing. They've been passing through this planet since before there was life on it, and they will pass through what remains long after. John Updike wrote that the Earth is just a silly ball to these neutrinos, and he was right. But we are the species that noticed they were passing through, and we worked out what they were. We also built instruments in the dark to catch them, and we're still learning what they have to tell us. And I think that is worth a lot of something. Thank you for listening to another episode of Space Bites with Benny. See you next time.